Hello, my name is Jared, and today I am going to be talking about relationships between heat transfer and mass transfer, and how I'm also going to be talking about wet bulb temperature and how humidity affects the wet bulb temperature. And then we're going to finish it up with doing an analysis of a cooling tower and to see how the temperature of a water changes throughout a cooling tower. And so the first thing that we're going to talk about is just the relationship between heat transfer and mass transfer. So when you take any situation, you want to model it, and you often model it with a differential equation. And in the case of heat transfer and mass transfer, both of those governing differential equations describing the situations have the same form, and that the heat transfer or mass transfer, I'll just write that as transfer the transfer is equal to some diffusivity so in the case of mass transfer, it is the Stefan-Maxwell diffusivity. In the case of heat transfer, it's the thermal diffusivity. So the heat transfer, mass transfer is equal to some diffusivity times a driving force, which is either a temperature gradient in the case of heat transfer or a concentration gradient in the case of mass transfer. So it's multiplied by some gradient, or I guess you could say some driving force. That's what we'll write it as. Some driving force. And this driving force is in the form of a gradient. And so for both of these processes, whether it be heat transfer or mass transfer, you have a governing differential equation because you have a gradient, which is just a derivative in one dimension. It's derivative with respect to the one dimension you're talking about. So ultimately you have a differential equation here. And since they're of the same form, you can expect the solutions to the equations to be the same. Although they're describing two different situations, the situations will be different, but both of those situations, if you contract it back to the governing differential equation, the governing differential equation is the same. So in the case of heat transfer, if you were to solve the differential equation, it would look like this. I did this in my last video too, by the way. Is you first non-dimensionalize it, and you'd get a equation of the form Nusselt number is equal to some real number A times the Reynolds number to some real number B times the Prandtl number to some real number C. And since the governing differential equation that you use to derive this equation here is the same for mass transfer, you can conclude that this same equation applies to mass transfer. It's just using a change of variables. So in terms of mass transfer, instead of Nusselt number, you get the analogous Nusselt number for mass transfer. In the case, that's the Sherwood number. And then you get A times Reynolds number to the B. Reynolds number applies to both the heat transfer and mass transfer, so that stays the same. But the Prandtl number, instead of the Prandtl number, you leave the analogous mass transfer Prandtl number, which is the Schmidt number. And what's important to note here is that these coefficients A, B, and C are the same. And that's what's really remarkable, is that you could practically do mass transfer experiments by measuring the heat transfer because they're directly correlated because of this. They're analogous because they have the same differential equation governing the situations. And so we want to talk about this thing called a Lewis relationship. So if you go about and get these two expressions here, and A is equal to A, B is equal to B, C is equal to C, well, let's just divide these two and let's see what we come up with. So if we get let's divide the Sherwood number by the Nusselt number. These all cancel out, and we're left with the Schmidt over the Prandtl raised to the C. Just like that. And yeah. I always just forget what the Lewis number is, if it's the Prandtl over Schmidt or Schmidt over Prandtl, so I just checked my notes right there. But this is the Schmidt over the Prandtl number is the Lewis number. So we can just say that this is equal to the Lewis number raised to the C. And so let's take this left-hand side and let's expand it out. So what's the Sherwood number? It's so Sherwood over Nusselt. What is that? Well, the Sherwood number is the ratio between the mass transfer coefficient with convection. So you write that as K sub C times some characteristic length over the mass transfer without convection. So that's just mass transfer, diffusive mass transfer. So use Stefan Maxwell diffusivity. So that's the Sherwood number. We divide that by the Nusselt number, and it's the same thing. It's analogous. But instead of it being mass transfer, we're talking about heat transfer. So we have heat transfer coefficient with convection. So we have H times some characteristic length, again, D, over heat transfer without convection. So that's just conduction. So you have conductivity here. We'll just leave that as K. So if we simplify that out, the D's cancel. We're left with K sub C over DAB, and then thermal conductivity over H, the overall heat transfer coefficient. And again, that's just equal to the Lewis number raised to the some power C. That's what we have right now. So let's look at what the Lewis number really is. So it's the ratio between the Schmidt number and Prandtl number. So the Lewis number, since it's equal to the Schmidt number over the Prandtl number, the Schmidt number is just the ratio between momentum transfer. So you have momentum diffusivity or kinematic viscosity over Stefan Maxwell diffusivity divided by the Prandtl number, which is again kinematic viscosity over, instead of it though being diffusivity, it's being alpha, the thermal diffusivity. So that's equal to, if you simplify that, it's equal to thermal diffusivity over Stefan Maxwell diffusivity. And the thermal diffusivity is just equal to the thermal conductivity over rho Cp, the volumetric heat capacity of the substance. And then we still have the Stefan Maxwell diffusivity over here. It just so happens that for a humid air, so for humid air, this expression here, it just, by coincidence of nature, it's approximately equal to 1. And you have to when you say it's for humid air, it wouldn't make sense to say for air or just any pure substance, because you see in here we have the Stefan Maxwell diffusivity, which is defined for a pair of species. It's not defined for a singular species, because in that case there would be no diffusion. So for humid air, the Lewis number is approximately equal to 1. Yeah, so that's basically just an air and water mixture. And since if the Lewis number is equal to 1 there, you can say that well, first of all, this isn't K sub C. I use K sub C as the mass transfer coefficient, so I should keep it consistent. I had thermal conductivity as K before, so if we look at the ratio between the thermal conductivity Stefan Maxwell diffusivity, that's just equal to rho Cp, or the volumetric heat capacity for air. And so if we go back to our original equation up here, we had the left-hand side is equal to K sub C times K over dAB times H. That's equal to Lewis number 2, the C power, so that's just equal to 1. So let's write the left-hand side. We'll just drag it down here. So we have mass transfer coefficient times thermal conductivity. We have Stefan Maxwell diffusivity over H. This equals Lewis to number to the C, but for humid air, that's just approximately equal to 1. So we say that's equal to 1. And so we can say that K over H, if we just simplify this, that's equal to dAB over mass transfer coefficient over the heat transfer coefficient is equal to Stefan Maxwell diffusivity over the thermal conductivity. Which, from before, it's just the inverse of this, so it's the inverse, the reciprocal of the volumetric heat capacity. So we get 1 over rho Cp. So this is the Lewis relationship. I'll just put it down here. The ratio between the mass transfer coefficient and the heat transfer coefficient is equal to 1 over the volumetric heat capacity. That's what the Lewis relationship is. And so when we're talking about mass transfer, we'll think about like evaporation of water. And so when water evaporates, that requires some energy. So that energy has to come from someplace. We'll discuss where that energy actually comes from in a second. Let's just first quantify what the actual energy is to evaporate the water. So you have the enthalpy of vaporization, which we can write down like this, lambda, and we'll keep that in we'll say it takes however many joules per kilogram of H2O that you evaporate. So for however many kilograms of water you evaporate, it takes this much joules of energy to evaporate it. So what is the rate of evaporation? And the rate of evaporation is just the mass transfer. So you have K sub C times concentration someplace times minus concentration, some concentration gradient, right? So this is concentration of water at some place, and this is the concentration of water at some place. And so we're going to consider the situation where water is evaporating, so it must be the concentration at the surface of the water must be higher than the concentration in the free stream air, in the ambient air. And so if we want this whole thing to be positive, it would have to be concentration of the water at the surface minus the concentration of the water in the free stream air. So we'll just say that as infinity. And so this whole thing right here is equal to moles per square meter per second. So that's moles of H2O. And so if we want to get to kilograms of H2O so that we can get joules per square meter per second, so like energy flux per second, we'd have to multiply this by the molecular weight. So we also have the molecular weight of water. Since we said that our enthalpy of vaporization is in joules per kilogram of H2O. We could have easily just said that the enthalpy of vaporization is joules per moles, and then we wouldn't have to multiply by the molecular weight. But we're going to say that the enthalpy of vaporization is in joules per kilograms. So in that case, we do have to multiply by the molecular weight. So this is the energy that is required to evaporate the water. So that must come from someplace. And so let's imagine a situation where you have water at, let's say you have water at some temperature and air at some temperature. Let's say that the temperature of the water is equal to the temperature of the air. And then water starts to evaporate. Well, as water evaporates, that takes energy. So that energy must come from someplace. So where can you get that energy from? Well, technically you could input that energy from like work, but in that situation of water evaporating, you're not inputting any work. There's no work being done on it. So there's no work being done. What about heat transfer? Well, if the temperature of the water is the same as the temperature of the air, then there can be no heat transfer since there's no temperature gradient between the air and the water. And so it'd be great to have some heat transfer. It'd be great to have the air transfer heat to the water to supply the energy necessary for evaporation. But in this situation where the temperature of the water is the same as the air, there's no temperature gradient. So tough luck, you can't get any heat transfer. So there's no heat transfer, there's no work being done. So, well, great, there's still going to be evaporation occurring, and that still requires energy. So if you don't have heat transfer, if you don't have any work, that energy has to come from someplace. And so the energy actually comes from the water itself. It loses internal energy. So the liquid water itself gives up energy to be able to supply the energy required for evaporation initially. But the interesting thing is that once the liquid water gives up some internal energy to evaporate the water, the internal energy of the water goes down. And as the internal energy of the water goes down, that means the temperature of the water decreases. And since the temperature of the water decreases, there's now a temperature gradient between the air and the water, and the air can now supply heat to the water. But again, since the temperature gradient at that point isn't necessarily high enough, the magnitude of the temperature gradient isn't great enough to supply the energy for evaporation. The liquid water still needs to give up some of its own internal energy. And so this is the whole process that occurs. The water keeps on giving up its own internal energy. It keeps decreasing in temperature, but as it does that, the heat transfer increases. And as the heat transfer increases, the water then has to give up less energy. So it decreases in temperature less. And this keeps on continuing until the temperature of the water gets so low that the magnitude of the temperature gradient between the air and the water is great enough to supply the energy required for evaporation. And since the heat transfer between the air and the water at this point supplies enough energy for evaporation, the temperature of the water itself does not decrease anymore, since it doesn't have to supply any more energy itself, because all the energy for evaporation now comes from the heat transfer. And so this temperature of the water that allows for sufficient enough heat transfer for evaporation, that's what we call the wet bulb temperature. That's why a swimming pool is always colder than the air around it. It's because there's water evaporating, and the temperature of the water just decreases until the heat transfer between the air and the water is exactly equal to the energy required for evaporation. So let's consider the situation where there is actually, we're at the wet bulb temperature, where all the energy for evaporation now comes strictly from the heat transfer between the air and the water. So that water itself isn't decreasing in temperature anymore, because the temperature gradient is enough to supply the necessary energy. So that's the energy balance that we're doing now. So we have, so this over here on the left-hand side is the energy required for joules per square meter per second. It's the energy required for evaporation, and that comes, we're saying in this equation, it comes strictly from the heat transfer between the air and the water. And so the heat transfer between the air and the water is just equal to H times the temperature difference. So temperature difference between the air and then the surface of the water, temperature of the water. So this is our overall energy balance for the case of wet bulb temperature. And so I'll see you in the next video where we will talk about, so we'll just circle this equation here. I'll see you in the next video where we will explore the adiabatic saturation temperature and then compare the equation that we obtained from that with the equation of this. And we'll see that this temperature here, which is the temperature of the water, where the heat transfer supplies enough energy for the evaporation, we'll see that the wet bulb temperature is approximately equal to the adiabatic saturation temperature. So I'll see you in the next video. All right, so now that we've talked about the Lewis relation and that the ratio between the mass transfer coefficient and the heat transfer coefficient is just equal to the reciprocal of the volumetric heat capacity, and that we talked about the energy balance for when the temperature of the water is at the wet bulb temperature, and that the energy required for evaporation is equal to the heat transfer between the air and the water. Now what we want to do is talk about adiabatic saturation temperature. And so what we're going to do here is we're going to analyze an experiment, do an energy balance on it, and then relate that equation that we obtain back to the energy balance for wet bulb temperature that we obtained. And then we're going to be able to end up seeing that the wet bulb temperature in this equation must be equal to the adiabatic saturation temperature, or it's at least approximately equal to the adiabatic saturation temperature. And so for adiabatic saturation temperature, what we have here is that we have a pipe, and the inner walls of the pipe are coated with some water, and the water's at some temperature TW. And then we blow air across through the pipe, and as the air blows through the pipe, there's some evaporation that occurs, and so the amount of water vapor in the airstream increases as it goes through the pipe. And we say that this pipe is sufficiently long so that there is enough time to the point where all the evaporation has occurred, and so that the amount of water vapor in the airstream leaving the pipe must be equal to the concentration of air at the surface of, the concentration of water at the surface of the water. And during this entire process, as the water evaporates, we continuously supply water at temperature TW so that TW stays constant. And since we do this, we know that the enthalpy in to the pipe must be equal to the enthalpy out of the pipe from a simple energy balance. And so let's just actually figure out what enthalpy in is, and enthalpy out will equate it, and that will be our ultimate equation or energy balance relation that we obtain for this problem. So let's do first enthalpy in. So enthalpy in, this would be to some like reference state. So you could think of like, so we have air at some temperature with with water vapor in it. Our reference state would be just the air with no water vapor in it and a temperature lower, which we'll just call that like 0, because it would just carry through and then it would cancel out in the end anyways. So like to get to the state that we're currently at, we would have to first evaporate water, increase the enthalpy of the air by evaporating water into it, and then increasing the temperature up to the current temperature from the reference state. So we have the enthalpy in would be the enthalpy that it would take to evaporate the current amount of water vapor in the air. That amount of energy plus the amount of energy to increase the temperature of the air-water mixture from the reference state temperature to the current temperature. So we can say that mass flow rate in, so we have the amount of energy to evaporate the water. So we have enthalpy of vaporization. So this is joules per kilogram of water. That times how much water do we have in the airstream coming into the pipe. So that could be, we could write something here that is in terms of kilograms of H2O per cubic meter of the air H2O mixture. So we basically just want the mass concentration of water vapor in the incoming airstream. So that's just the partial pressure. We'll call this state 1 and this state 2. So we'll say partial pressure of water at 1 over RT. That's moles per cubic meter. So we just multiply it by the molecular weight of water, and that would give us kilograms of H2O per cubic meter of air, air-water mixture. And then we multiply that by the specific volume of the incoming airstream. So that would be, we're going to input something here that is the cubic meters of air H2O mixture per kilogram H2O air mixture. So that's just the specific volume, which is inverse of the density. So it's RT over the total pressure. And then we also have average molecular weight. So that has to do with the energy of the water vapor in the air. How much energy would it require to evaporate that much water into the air? And then we also have enthalpy in the terms of like the temperature of the entire mixture. So we have specific heat capacity for the air-water mixture and times just the temperature that it's at. So this is the enthalpy we have coming in. If you notice, if you follow out all these units, you end up getting with, from this whole expression right here, let's consider that you get joules, kilograms H2O, that cancels out, this cancels out with this. So your joules per kilograms of H2O air mixture. And the mass flow rate in, we have in terms of air, so it's kilograms of air per second. And so really what you have here is joules times kilograms of air per kilograms of air water mixture coming in per second. And you just make the approximation that the kilograms of the water air mixture is approximately equal to the kilograms of air coming in, because there's way more air than there is water. So that's the approximation we make. Otherwise, we would have to convert all of this kilograms of the kilograms of H2O air mixture. We'd have to convert that to kilograms of air if we wanted like an exact conversion. But we're engineers and we approximate, so we're just going to say that the kilograms of the total mixture is approximately equal to the kilograms of air, since majority of the mixture is air anyways. So then we do the same thing for enthalpy out, and same explanation would suffice for this as the first one. So we're just going to use the same thing. Just note that the mass in is equal to the mass out since it's at steady state. So you get mass flow rate. I guess instead of saying mass flow rate in, I'll specify that as mass flow rate of air. Mass flow rate air. And then we're going to get the same thing, except we're going to change the pressures and the partial pressure. So we have lambda partial pressure of water leaving, but since we said this was sufficiently long, that's just the saturation pressure of water at the temperature of the water. RT, get the same thing, P total, M average, C sub P. We also say that the specific heat capacity for the air-water mixture is the same because the amount of water in it doesn't change the specific heat capacity since the majority of it's air anyways. So enthalpy in equals enthalpy out, and when we do this, I'll do some algebra here. Let's see, we'll have lambda. Well, first of all, I forgot molecular weight of water right there. So we have lambda molecular weight of water over P total molecular weight average. So I'm combining the enthalpy of vaporization of the waters. So this term with this term, that's what I'm doing right here. P saturated partial pressure of water at TW minus partial pressure of water at the inlet. That's equal to C sub P. Let's see, I carried, that's on this side, so it must be T1 minus T2. I'm just making sure that my algebra is correct because I skipped some steps. Okay, cool. Yes, that's what I obtained before. So this is the ultimate equation that we got for the energy balance for adiabatic saturation temperature. And the adiabatic saturation temperature is the temperature of the outlet air-water mixture from this pipe. So that would be T2 is the adiabatic saturation temperature. Now we're going to take this equation here, and how does it relate to our equation we had up here? And what we're going to see is that they are the same. And so how we're going to do that is, well, we could either, if they're the same, then like symbolically they must be the same. So we can either take this equation and convert it into this equation that we just came up with, or we can take this equation and convert it to this one, whichever one we decide to do. And in doing those conversions between the two equations, we're going to have to take use of the Lewis relation. So the way I'm going to do it is I'm going to take this equation right here, and I'm going to expand it out and use the Lewis relation until I obtain this equation here. And we'll see then that this wet bulb temperature must be equal to the adiabatic saturation temperature. And so I'll do that now. So I have this equation here. I'm going to write down the energy balance for the wet bulb temperature again. So I had lambda times molecular weight of water times Kc Then I had the concentration of water at the surface in moles per cubic meter. So that's just saturation pressure of the water at TW over RT minus the molar concentration of water in the air. So that's just partial pressure of water in the air, infinity we'll say, RT. So this is just the molar concentration difference between the surface of the water and the free stream air. And that's equal to H times T infinity over TS. So all I did here was I took this equation up here and wrote it down here. Except that I made these molar concentrations, I expanded it out using the ideal gas law to save some writing room, because eventually I'm gonna have to do it anyways. So now we can take this Kc and divide it over, and we have H over Kc, and using the Lewis relation, H over Kc must be equal to the volumetric heat capacity. So on the right hand side, we'll have the volumetric heat capacity. So we have lambda times molecular weight average equals, we took Kc to the other side, the mass transfer coefficient. So we don't have that on this anymore, on this side. TW, RT, and equals what? Volumetric heat capacity times T infinity minus TS. Now what we're going to do is just, again, all we're trying to do is take this equation. It's looking closer to this. We have PSAT, we have RT, lambda molecular weight. It's looking closer to this, so we just want to expand it out more, and what we're going to do is expand out the density or the total mass concentration. So that's equal to, let's write the left-hand side again. Total mass concentration, it's the total molar concentration, which is P total. This is using the ideal gas law. So P over RT equals N over V, which is N over V is the molar concentration, but we want mass concentration since we're talking about density, so we also multiply by the average molecular weight. And then we have C, the specific heat capacity, and then we have the temperature difference. And RTs we see cancels out. Take P total, M average over to the other side. Get lambda M molecular weight of water over P total times molecular weight, average molecular weight times PSAT, saturation partial pressure or vapor pressure of water at the temperature of the water, times the partial pressure of water in the air is equal to C sub P times T infinity over TS. So this was our energy balance equation. Don't forget, this was the energy balance equation for the wet bulb temperature. And now if we take this equation, all we did was we expanded out the wet bulb temperature energy balance equation. We expanded it out till we got something that looked similar to what the energy balance equation we got for the adiabatic saturation temperature. And we see that these left-hand sides are the same. And so T infinity minus TS, so T infinity corresponds to T1. It's just the temperature, it's the dry bulb temperature, just the temperature of the ambient air. So T, temperature of the water, which we said was the wet bulb temperature. This wet bulb corresponds to T2, which T2 in this equation was the adiabatic saturation temperature. And so from this analysis, we can say there were some approximations, but practically the wet bulb temperature is equal to adiabatic saturation temperature. All right, and now I'll see you in the next video where we will take this concept of evaporative cooling and we'll apply it to a cooling tower, and then we will do differential energy and mass balances on the cooling tower to derive differential equations describing the mole fraction in the airstream in the cooling tower as it changes with position, and also come up with a function describing not only the temperature of the air but the temperature of the water. So we'll do that in the next video. I'll see you there. All right, so now what we are going to talk about is evaporative cooling in a cooling tower. And so we have a cooling tower here, and it is packed with some stuff, and the area then of water, as water flows through, the surface area of water that is exposed to the air, it's represented by this. It's little a. It's area exposed to air over cubic meter of volume. So basically, how much surface area of these packed particles do you have per unit volume of your tower? And then we have water coming in, and we're going to represent that by big L. It's kilograms per second per area, and that area is just a cross-sectional area of the cooling tower. Same thing, we have the gas flow rate in. That's air plus water. That comes in, and that is also just, the units of that is kilograms per second per square meter. And again, that area there is the cross-sectional area of the cooling tower, which is important to take note of because there will be two different areas that we're talking about here. One of them is area, which is the cross-sectional area of the cooling tower. The other area we're talking about is the surface area of water that is exposed to the air, that area will be used for heat transfer, mass transfer. But in terms of like mass flux through the cooling tower, these areas here, those represent the cross-sectional area. So you just need to keep note of what area you're actually talking about. Otherwise, you'll end up deriving something that is incorrect. So ultimately what we want to do here is we want to we want to come up with equations for the mole fraction of water in the gas phase as the gas flows up. And we'll just denote this direction here as Z positive. So this is one-dimensional. This direction here we'll say is Z positive. So liquid water comes in and then comes out here, this being 0, and then however long the tower is, it'll be whatever that is, but it'll be positive down here. So this is the positive Z direction. So we want to come up with how the mole fraction of water in the gas phase, how that changes with respect to Z. So as gas flows up, there'll be evaporation occurring, and so there'll be more water in it. So you expect the mole fraction to increase in the gas phase as it comes up. We also want to derive an equation for the temperature of the water. So as the temperature of the water comes down, assuming that the temperature of the water is not at the wet bulb temperature, the temperature of the water will decrease as it evaporates. It will decrease until the wet bulb temperature. So you expect that the temperature of the water, as it goes down in the positive z direction, it will decrease because it will lose internal energy to supply then some of the energy required for evaporation to occur. And then we also want to come up with a function for the temperature of the gas phase. And as the gas comes up, it supplies heat to the water. So you expect the temperature of the gas as it goes up, assuming that it is higher temperature than the water, it would supply heat to the water for evaporation, and so it loses energy, and so the temperature of the gas would decrease as you go up the column. And to not get like too involved with symbols here, I really want to explain how we come up with these equations, but we want to I want to explain it conceptually and not symbolically. So I will say something conceptually, and then I will write it down symbolically without really, I'm not going to explain every step symbolically, because that isn't the point of everything. The point of it is to be able to get it conceptually of what is going on. You explain an equation in English words, and then you represent those English words with symbols, which are just derived from textbooks. But what you want to do as an engineer is be able to know what is going on conceptually. So that's an important part. That is what I'm going to be highlighting. So if we want to come up with an expression for the mole fraction of water in the gas phase as we go up the column, we can't derive that directly. So we have to model it. And when we model things, we talk about how things change, and we model things with differential equations, because differential equations describe how things change. So what we would do is take a differential volume here, so a volume that has the same area as the cooling tower, but has a differential projection in the z direction. So it's like dz, so the entire volume, the differential volume that we're talking about is the area times the little bit of change in z. And so just remember that when we're talking about z, we're talking about how does it change with z is going down the tower. So if we talk about with how does the amount of water in the gas phase change with respect to z. So let's talk about like a small change in the amount of water in the gas phase with respect to z. What's that equal to? So that's equal to something. We'll start with that on the left-hand side. So symbolically, that's just, well, how do you represent the amount of water vapor in the gas phase? It would be the gas flow rate, which is kilograms per square meter per second, times the cross-sectional area of your cooling tower. That gives you kilograms of gas per second. Convert that to moles. So you'd have to divide by the molecular weight, average molecular weight, and then the mole fraction of water in the phase. That is the amount of, that would be the moles of water going through any area per second. So how does that change? Like a small change in that, if we're talking about like going in the z direction. Well, as the water comes down, right? So if we're talking as the gas, if we go down here, we expect that the amount of moles, the amount of water to increase as the gas comes up, but we're talking about going in this direction. So if it increases in this direction, it must decrease in this direction. So first thing we know is that this is negative. And so how much does that change? Well, the increase or decrease in the number of moles of water that are moving through the cooling tower in the gas phase and the vapor phase, well, that's just the mass supplied from evaporation, because there's evaporation occurring. So it's equal to the evaporation rate, so Kc times concentration at the interface of the water, and the gas minus C infinity, the concentration, right? So this over here, let's just make sure, important thing to do here when you're going from conceptually wise to symbolic is like to know you have to make everything dimensionally homogeneous, meaning the dimensions, units on one side are equal to the units on the other. So let's just make sure. So this over here would be moles of H2O per second, and over here the units of this is moles of H2O per second per square meter. That's why you always have to check for, make sure that it's dimensionally homogeneous. So we note these are not the same, so we have to get rid of the square meter on the side. On this side, the right-hand side, that square meter is the surface area of water. So to get rid of that, we can multiply by A. We get rid of the surface area, and then we have cubic meter of volume. And then we just multiply by the volume of our differential volume, and then we'll get rid of it. So we also have to have A here. That will give us moles of H2O, moles of water per second per cubic meter of volume. And then we multiply by the volume. So we also have cross-sectional area times dz. So this is our first equation here. If we want to express this in terms of a differential equation, we can just assume that area does not change, gas flow rate does not change, average molecular weight does not change, so we can take it out of the differential. And simplifying it, you can do that on your own. That's dy dz. How does the mole fraction change with respect to z? Is negative Kc Ci minus C infinity. The A's cancel out. So we also have A over here. And then we have G comes to the other side. And molecular weight. Let me just make sure I'm doing this algebra right. A molecular weight for G. So we also have the molecular weight, average molecular weight here. I'm just skipping steps because hell, if we're doing this, we don't need to explain the algebra anymore. So this is our first differential equation. This is the governing differential equation that explains, that describes the mole fraction of water in our gas phase. Okay, and now if we want to describe how does the temperature of the gas change or the temperature of the water change? Well, the gas, the air, so you have air coming in with water. How does the temperature of the air change? The air supplies energy for evaporation, so as it supplies energy for evaporation, you expect that the enthalpy of the gas must decrease. So I think the simplest thing is to first define a differential equation describing how the temperature of the gas changes, because that's easy, because the change in enthalpy of the gas is just equal to how much energy it loses, and it just, how much energy it loses is just the heat transfer. It supplies heat necessary for evaporation, so that amount of energy comes from the enthalpy of the gas itself. So a small change in So how does the enthalpy of the gas change? So let's just write how that is. So you have the gas flow rate. So that's kilograms per square meter per second. You multiply that by area, you have kilograms per second. And then multiply that by specific heat of the gas. And then times some small change in temperature of the gas. That's the change in enthalpy of the gas over a small amount of direction, like a small distance in the z direction. That's how the little change in enthalpy of the gas. So it changes. Why does it change? Where does that come from? Well, it's equal to how much energy it loses or absorbs, and that energy that absorbs or loses is just heat transfer. That's only energy transfer going into the gas or out of the gas is the heat transfer. So it's equal to the heat transfer between the air and the water. So we can write that as H times temperature of the gas, which will say T infinity over T temperature of the water. Well, T infinity, I guess we'll just call it TG. T water. So let's just, again, make sure. So over here on this side, we have kilograms per second. Then we have joules per second. So this is joules per second. Whereas this is joules per square meter per second. And that square meter, again, is equal to surface area, because the heat transfers are coming between the surface area of the water and the gas. So to get rid of that, we just, again, do little a, which is the area of your packing material exposed to the air over per unit volume of your cooling tower. So A dz, just like that. So temperature of the gas as it goes in the z direction. Well, as it goes up in this direction, right, it gives heat necessary for evaporation. So you would expect as it comes, temperature of the gas as it goes up to decrease. Therefore, as you go down, it must increase. Opposite. So this would be correct. You want this to be positive on this side. So if we just, again, algebraically, we're just going to simplify this to a differential equation where we have derivative of the temperature of the gas with respect to z. And when we do that, we should get derivative of the temperature of the gas with respect to z is equal to h tg minus tw a HA, we also have GCG. So this is our governing differential equation for how the temperature of the gas changes with respect to Z. Let me just make sure how that compares with my notes, making sure I derive that correctly. AH, GCG, TG over T water. Yep. Okay. I just want to make sure because especially with like sign errors, that will propagate through the entire problem and then you'll end up getting something that's completely ridiculous. And so not only do we expect that the enthalpy of the gas to change, we expect the enthalpy of the water, liquid water, to change. So how does that change? We'll express it the same way. So we have liquid water. That's kilograms per square meter per second. We multiply that by the cross-sectional area of the cooling tower with kilograms of water per second times the specific heat capacity of the liquid water times the change in temperature of the water. That's equal to, okay, so the enthalpy of it changes. We're talking about as it goes down. It absorbs heat from the gas. So you have supply of energy from the heat transfer of the gas to the air. I mean from the gas to the water. So that's one thing. So we can write that as just H TG minus, I'm pretty sure it's just the same thing as we had up here. It's exactly this. Yeah, so HAA TG minus DWDC. So it's exactly the same thing. Let's just make sure that, again, we're being dimensionally homogeneous. So this over here is kilograms area second, kilograms per second, joules per second per, so this over here is joules per second, whereas this over here is joules per square meter per second, joules per second. So yeah. So as the water goes down, you expect its enthalpy to increase because there is a supply of energy from the gas to the liquid. That is, there's heat transfer between the gas and the liquid. So that's what this is right here. And then we also lose enthalpy because there's some vaporization occurring. So we just need like joules of second of enthalpy that's leaving due to evaporation. So I'm pretty sure I wrote that down somewhere. I think it's this right here is the rate of evaporation, moles per, this whole thing right here is moles of H2O per second. So if we write that down here, the same thing. Okay, say C minus C infinity. So I'm just writing down that exact same thing. That right there, this whole thing is moles of water per second. Multiply that by the enthalpy of vaporization. So we also have enthalpy of vaporization here, whereas the units of the enthalpy of vaporization is joules per mole. So this is the equation, governing equation for how the temperature of the water changes. And if we simplify that out, again, all this is now is just algebra. So I guess conceptually, I'll just explain it again real fast for the temperature of the water. The temperature of the water, it decreases the amount of energy that decreases by, that's because there's absorption and desorption of energy. So energy comes in from heat transfer between the gas and the water. So it absorbs this energy, which it causes the temperature to increase. But then it also loses energy because there's evaporation occurring, and it loses the energy associated with that mass, because what we're talking about here is the temperature of the liquid water, not temperature of the water in general, because the water is in two phases. So it wouldn't make sense. This is the temperature of the liquid water. So if we take this whole expression here and we simplify it algebraically, we should be able to get, let me see, d dz is equal to I already worked this out before, so I'm literally writing down what I see on my notes here, which I guess is cheating, but I think you can be convinced that I can do some simple algebra here. I just don't feel like doing the algebra right now. Minus lambda NW. Which I know what that was. So essentially, this is the differential equation. If you simplify it, I didn't feel like doing it in my head right now because I'm on camera and I might mess it up. So I did just copy it from my notes. Call it cheating, call it not. I know what's going on conceptually. I could describe it symbolically. Algebra can be confusing. I just wrote it down from the paper. So this is what's going on, the change in temperature of the water, right? You have, it's changing because it's absorbing heat from the air, but it's also decreasing because it's losing enthalpy, because it's losing the energy associated with the mass that it's losing, which is this term here. And so these are our three governing differential equations describing how the mole fraction of water in the gas phase changes in the z direction, how the temperature of the gas changes with respect to z direction, how the temperature of the liquid water changes with respect to the z direction. So we have these, we derive these by hand, and now in the next video I will go through and solve these. I will input parameters to these and then solve these differential equations for a specific cooling tower and specific initial conditions of the gas and liquid water. And I'll be able to find these functions describing the mole fractions and temperatures. So I'll see you in the next video. Thank you.